Okay. Okay, what is the dang? Let me get this. What would that be? Sorry, I'm all disorganized this morning. Quit that. Dang it. Screw it. Screw it. I don't think I'm going to be able to get it done. I don't know. I don't know. Remember the old days when I could just walk into a classroom and start teaching without all this malarkey? Annoying. Annoying. After all this time, I still don't know how to properly set up a Zoom meeting. I just don't. Oh, and I can't see. Okay, where's the little hole? There it is. I don't think I see this right. Got one person here. I must have done something wrong. Go back to there. Go back to Blackboard. Cancel. Come on. All right, where'd Blackboard go? May not be the right one. How do I do this? A lot of people missing, so they're probably waiting for me to get the Zoom thing set up right, and I'm just not doing it right.
The Zoom is set up, at least on my end.
Let's see. All right, where's this stupid thing? Why don't I pass back your tests? That way you can at least do something while I'm standing up here testing this machine. Maybe, where's the other thingy? Okay, quit that, get small again. The link on Blackboard leads here. Thank you, Reed. But I just changed the link on Blackboard, so I may have screwed it up. I may have screwed it up on HoverCam. Start the video. Why not? Cancel. Okay, let me pass back your test. Please come get them when I call your name, because I'm kind of doing two things here. Ariel? Morgan? John? St. Andre? Neil? William? Noah? Andrew? Lisa? Ethan? There we go, something's working. Annie? Got Evelyn? Caleb? Nathan? Shelby? Jacob Conrad? Daniel? Rohan? Tanya? The score that's in black is the score after the corrections. Okay, why don't you have this camera device going? Let's see who made it to Zoom here. I did something wrong. Let's see if it worked. There's my stupid meeting. Uh-oh, it's not good. There's only one of us. That's bad. Let's get out of this one. Okay, that's not a good one. Stop this one. How do I get to this meeting? Okay. But that one doesn't do the other one. Nope, this is not good. This thing didn't work anyway. All right, Reed, can you hear or see anything? Can you see the little green thing on the screen? Maybe, no? You can see me, but not the green thing. Bummer. I think we got the wrong link then, Reed. I gotta find another way to get this out. Okay. Fudge. Why is it doing that? Where's my computer whiz here? Let me see what this is. Open. Let me do this one. Okay. All right. Who knows how I get the address to this meeting?
It's probably in the Zoom call itself.
This thing
At the bottom.
here? No. It's
It's like the thing
This
that's
thing?
flashing orange at the bottom.
thing that's flashing at the bottom. Where?
Like the orange.
This thing?
Yeah.
No, that's the.
Oh, never mind. That was just the
I
chat.
can see you and hear you. Couldn't you share your screen? Well, I've got it shared on a different Zoom meeting. So that's, so Reed, I've got you on a Zoom to me, but not to my little goofy machine. So I'm looking for the address to the goofy machine maybe. Or, does any of you know how I can get this, go to this one? What was that? I don't know what that is. All right, Reed, can you see the little green screen now? No, okay. So I've got the wrong link. You've got a different link than I've got up here. So I gotta figure this out. And all I know how to do is cuss. Okay, that's not good. Go back to main window, that's us. Okay, that didn't help me. How do I know where I am?
Oh, excuse me, Professor. Could you share this camera screen directly through Zoom by using the share application for like a specific window in Zoom?
That might work actually. Yeah.
Oh, okay.
Come save me.
Okay.
So we can go to Zoom and then here will be a share screen.
Okay,
So if we click that, so you can participate and share the time. Yeah, it's good. And then this window
That one.
specifically. So we share camera and now in Zoom, they should be able to see this.
okay. Alex, can you see this, Reed? Can you see this, Reed?
Yes.
It's at the top.
It works, yay, my hero.
Not do that.
That was as close as I could get to hugging you. Okay, now there's other people wanting to know how to get here. And so I guess I'm gonna send them this thing. So, and then I gotta go record this son of a biscuit. Okay. Something's recording, so that's good. All right. I think that's the link I sent. I'm going to try it again. Okay, that's working. And I was going to share this with everybody. A lot of folks missing. Trying to get this going. Okay, eventually we're going to start. Okay, nail, where's my nail? Pop it down there, nail. Oh, except now I lost my link. And I'm going to find it again. And it runs in my little chat box. I'm going to put it in my mail. Whoops. Okay, that's taken care of. Now, if anybody else shows up, super. Hey, Esther made it. Woo! By gosh, by golly. Anybody bring anything to drink? No, I'm not particular. Just a shot. Okay, I want to talk about the test a little bit. So let's see. February 21. All right. Why aren't you showing? Okay. Okay.
It might be this. Just click cancel at the bottom.
Cancel. Okay, that didn't help. It's still showing the green thing. One screen sharing. Is it not letting me? Okay. People are coming though. That's good news. But all we can see is the green thing. What's down here? Nothing. Okay, don't want that anymore. Okay, who's got the solution to this one? System error, thank you. Appreciate that. Son of a biscuit. It's doing something. There's the little circle of doom. Okay, well, let me just talk while I panic. This is about the place in the semester where in the spring, everybody went home. So I started making about 30-minute videos for the class over each topic. So the instructions to them were to read the book, watch the video, and then we'd have a class. So in other words, you have access to those now. In addition to what I'm going to do in class, I'm not going to stop class, but they're there on Blackboard in the little folders. You can click on the link and it takes you to a YouTube video, and they're kind of a mini version of a lecture, so you don't have to watch a big 2-hour thing. Imagine these 2-hour jobbers are boring, especially when 20 minutes of them is looking at nothing. But why? Okay, I still got some sort of infinite circle here. Might have to do this full zoom. Okay. Got 6 people watching nothing. That's good. That's absolutely great. Don't want that because I got that. I think it's crashing. I think it's crashing too. Okay. Well, I can see part of the board. Maybe I'm just right on the board. Okay, I wanted to work some of these. I don't know about this stupid thing here. Let's just get the screen up for a while. Then I got a marker. One of the problems that I did want to work was I put a note on here, was number 14B. Let me see if they can see this if I write it.
Oh, it might be mirrored.
It might be mirrored. What does that mean?
Like,
Oh,
what they're gonna
backwards.
see is gonna be.
Nope. Yeah, crud. Yeah, I'll just go back to that. Look, I've got two of these here. Why? One,
That's what. Yeah.
I know. So this one goes with which one? I don't want
That's the one, that's the right one.
That's the right
The
one.
one in the middle of your screen is good. I think the one on the like slightly left side is part of the thing that's crashing
I
right
think
now.
you should close that.
So I think if you just close that maybe, and then reopen it without starting a Zoom, you might be able to just share it from the other Zoom, and then it should be okay.
But now I can't record it.
But then I think this Zoom maybe can record it.
Okay. Okay, and so here's the current, do I have a Zoom still open?
Yeah, that's the one.
Yeah.
That's this one. Okay. And so
It's a reopen.
it's recording.
Yeah.
That's good.
So then
And I'm going to share the screen.
yeah, you have to reopen
should
the.
reopen the-
Oh, that stupid thing first. Okay. Is this like teaching grandma how to use her phone? Quit!
You can minimize this.
No, you
Okay.
can't.
It's funny.
Now get out of the way.
Just move
I
it
think,
downwards.
yeah, move it downwards instead of upwards. If you hit it against the top of the screen, then it full screens.
No,
Okay,
but look.
now, yeah,
Yo!
okay, now it works. So then
Okay.
I think you
Go
can,
back to Zoom.
now you've got to do the screen share from the other
Go
Zoom.
back to Zoom.
Go back to Zoom, but which Zoom? This Zoom, that Zoom,
That's,
That one, yeah.
that Zoom, and we're gonna screen share.
Yes.
And here,
and then,
no. Okay, everybody at home, can you see the little green screen with the white test paper?
make sure it can move around.
Yes,
You put your
good
hand down.
job.
Yes, yes, okay, all my 6 participants. Can anybody see what's going on? Where's my little chat?
Okay, cool.
Everybody's good? Okay. All right. So I was going to work number 6B. So I'm going to do that on a blank piece of paper. Take you through the steps there. Because we're going to see this problem again in chapter. What chapter are we in? 8? Okay, so we're asked to take the limit of 1 minus 2 divided by n all to the n. I guess I need my screen back down. That is. And when we talk about limit, it's as n goes to infinity. And so starting inside the parentheses as n goes to infinity, 2 divided by n is going to go to 0. So in the parentheses, I have 1 to the infinity. Now that's an indeterminate form, and we handle that indeterminate form by using a logarithm. So I first make an equation out of this. I'm looking for limit L, but I'm going to find the logarithm of the limit. So I'm going to take the natural log of both sides. And then I'm going to bring the n down in front. So it's no longer in the 1 to the infinity indeterminate form, but it is still an indeterminate form. This term is going to infinity here. This is going to 1 in here, and the natural log of 1 is 0. So it has the form of infinity times 0. We're trying to put it in either 0 over 0 or infinity over infinity so that we can use L'Hopital's rule. The polynomial term is going to go on the bottom as a 1 over n, and that's going to put it in the right form. Multiplying by n is the same thing as dividing by 1 over n. And now the numerator goes to the natural log of 1, which is 0. 1 over n goes to 0 as n goes to infinity. So it has the right form for me to use L'Hopital's rule. I take the derivative of the top divided by the derivative of the bottom, and then whatever limit we get there will be our limit. The derivative of the log of u is 1 over u times u prime. So let's think of that minus 2 over n is 2n to the negative 1, and we'll get positive 2n to the negative 2. Downstairs, 1 over n is n to the negative 1, so we get minus n to the minus 2. I can cancel the n to the minus 2's. That leaves me a minus 1 on the bottom and a positive 2 on top. So I'm going to write that as a minus 2 on top. So the numerator is a constant. It's not affected by n, but the denominator has the 2 over n, which will go to 0. So this limit here gives us a negative 2. The natural log of our limit is negative 2, tells us our limit then is e to the negative 2. So this sequence converges to e to the negative 2. So that was problem 14b. The other problem I wanted to work was 12b. And you're asked why this integral from 0 to 4 of dx over x minus 3 squared is improper. And this is the improper integral of type 1 in that the integrand has a discontinuity within the limits of integration. So it is improper because 1 over x minus 3 squared is not defined at x is 3. So we're going to try to integrate around 3. We'll break this integral up from 0 to 3 and then from 3 to 4. But now I'm going to use a letter for each of those 3's. Usually my limits are from A to B, so I'm going to say I'm going from 0 to B. Then we'll let B go in toward 3. It's coming in from the 0 side, so it's coming in from the left. Then I'm going to replace this one with an A, integrate from A to 4, and then take the limit as A goes to 3 from the right. In each case, we're integrating u to the negative 2 du. And we can just do that by adding 1 to the power and dividing by the new power. So we get negative 1 over u. In our case, u was the x minus 3. So here I'm going to take the limit as b goes to 3 from the left of 1 over x minus 3 from 0 to b. That's going to behave the same way, so I'm going to kind of blow that off for now. If I put the b in there and the 0, I get this plus the other one. But I don't need the other one because I can see as b goes to 3, the denominator here goes to 0, which means this first fraction blows up, goes to infinity. So this term gets infinitely large, and so this limit does not exist, which means the integral diverges. No matter what happens in the second one, the integral is going to diverge because the first part did. But the other one behaves exactly the same way. Does that make sense? Okay, do you want to see me work any of the other ones? Anybody? We did kind of jiggity corrections on them. I was kind of in a hurry. All good? For the most part, I think you guys did an excellent job. I didn't look at the average, but I did put the average on Blackboard. If you do want to see any of these, I can scan my key and send it to you. Okay, so let's see where we are for the rest of the semester. We've got section 8.2 today. Today. I'm going to give you an introduction to an infinite series. And then I'm also going to start section 8.3. Section 8.3 talks about something called the integral test and introduces to a series called a p-series. We've got another test scheduled before we leave for Thanksgiving. Test 3 is November 23rd. And that will be in class. And that's the Monday of Thanksgiving week. And I hope it'll cover all of Chapter 8. There are 7 sections in Chapter 8. And then after the Thanksgiving break, we don't come back, but we've got 4 sections of Chapter 9 that we'll do online somehow, this version kind of crap, where nobody's there to help me when things go wrong. The 4 sections in Chapter 9, I think, for most of you will be relatively easy because that's just introduction to vectors. So, but this Chapter 8 stuff is pretty important. We're talking about an infinite series. We've seen sequences, which were a list of numbers. A series is the sum of those numbers in the list. We're going to take our things. So let me write the notation that we've got. When we put them in the cute little brackets like this, we had a sequence. And it's just a list of numbers. And we said a sequence converges if it has a limit. As n goes to infinity. We pictured a sequence as a graph of dots, kind of like a scatter plot. And so if in your scatter plot, as you read down the counting axis, the n axis, if all of the dots kind of hover around the same horizontal line, then we said that the sequence converged. So here's my counting axis, that's n. And so for n is 1, 2, 3, and then maybe k plus 1. If we had a sequence of dots here, and then they kept going on and on, if after a certain while they all started behaving the same, then we said that that sequence converged to that limit L. A series is much more complicated than that because we're adding things together. A series is the sum of terms in a sequence. So it'll look like A1 plus A2 plus A3. Maybe we're out here at AK plus 1. But it goes on forever. It's a sum. And we denote a series, the sum of the terms in a sequence, by using this capital letter, that's the Greek letter sigma. That says add up things that look like that general term AN. Sometimes our counter will start at 1, sometimes at 0. It could even start at 20. Over here we tell the reader what the counter starts at. Doesn't matter where you start if you're adding an infinite number of things together, right? So I've written this one so that it is from 1 to infinity. We will use series in engineering and in science to represent functions. A function is a continuous curve, but we can relate series to functions over small intervals so that this sum converges to the function, behaves just like the function does. That means if we have something that we don't know how to differentiate or don't know how to integrate, we write it as a series, special kind of series called a power series, so that it has a variable in it, and it's stuff added together that looks like a polynomial. We can do anything to polynomials. So we're building these things to help us with functions. But for the most part, here at the beginning, we're just dealing with adding a bunch of numbers together. And we want to know when that sum is going to be finite. So we're going to picture a series as little sticks that we're adding together. Let's take the terms in that would be a sequence, something like that. Now, if we're adding them together, we're adding how tall these, what would be y values are. We're going to add these sticks. And if we place these sticks on top of one another, one after a time, will that height essentially terminate? Will I have a finite sum, or will it grow forever? If it has a finite sum, then we say the series converges to that sum. If they grow forever, then the series is going to diverge or become infinitely large. If the sum is finite, then we say the series converges, and it converges to that sum. Otherwise, we say the series diverges. Or has an infinite sum. One of our main tasks in this chapter is just to make the determination, does it converge or not? We'll very rarely be able to find what it converges to. That's typically done by manipulating the series on a computer. But there are advanced ways to find some of the sums. But for us, that's way beyond the scope of what we know how to do or will know how to do with calculus 2 techniques. Need a lot more arsenal to be able to find what they converge to. So just being able to say whether the series converges or diverges is our primary goal. Here's an example of a convergent series. One plus a half plus a fourth plus an eighth plus 1/16. Add those things forever is converging. I'll show you this in a minute. The series very similar to that, say 1 plus a half plus a third plus a fourth plus 1/5, that series is divergent. Not much of a difference. In the first series, I put just the powers of 2 in the denominator. In the second series, I just put the counting numbers in the denominator. One grows infinitely large, one doesn't. One adds up to a finite number. Pretty freaky, huh? Now, if I take an infinite sum and stop at some place, like if I add the first 3 terms here, 1 plus a half plus a fourth, I'm going to get a finite number. 1 1/2 plus a fourth is, I don't know, 4/4, 2/4, 6/4, 7/4. That 7/4 is called the third partial sum. Added 3 terms together. If I go out to add 5 terms together, I've got the 5th partial sum. If I add out the first n terms, I have the nth partial sum. Let's let Sn denote the sum of the first n terms of the series. I'm going to use a K here. Okay. So I'm saying that Sn looks like A1 plus A2 plus A3, and then I stop out here to AN. So we're going to call that the nth partial sum. Depending on what I choose for n, in fact, if I let n be 1, 2, 3, 4, 5, and so on, I can make a sequence of partial sums. Then this, when I put it in the cute brackets, is a sequence of partial sums. Right? It's a sequence that looks like S1, S2, on out to Sn, where S1 is just the sum of the first term, S2 is the sum of the first 2 terms, S3 is the sum of the first 3 terms, and so on. I can make a sequence of partial sums. And our first theorem in this section says that if a sequence of partial sums converge, then the series will converge and to the same thing that the sequence of partial sums converges to. Okay, so let Sn be the nth partial sum of the series if the sequence if this Sn converges, then so does the series. So in other words, if the sequence of partial sums has a finite limit, then so does the series. This is going to be the underlying theme of how to find the sum of a series, except it's hard. That's the theory. The practice is kind of hard. You have to have something that's kind of set up for you in order to be able to see if these sequence of partial sums converge. So I'm going to go back to the first one that I said, 1 plus a half plus a fourth plus an eighth, and show you how I can figure out that that converges using this theorem. And we will show this converges by showing that the sequence of partial sums converge. It's really bad handwriting today. I'm not a big fan of writing with pen. Anything else I can write with? Okay, so here's S1. S1 is just the sum of the first term. S2 means I'm adding the first two terms together. So 1 plus a half is 3 halves. S3 is the sum of the first three terms. 1 plus a half plus a fourth. So that's 3 halves, or 6/4 plus 1/4 is 7/4. S4 is 1 plus a half plus a fourth plus an eighth. So if I take my 7/4 and add an eighth, that's 14/8 plus 1/8 should be 15/8. And I've got room to put one more here. S5 is 1 plus a half plus a fourth plus an eighth plus, let's see, that'd be 2 to the fourth, 1/16. So 15/8 plus 1/16 is 30/16 plus 1/16 is 31/16. If you look at those numbers that I generated across the equal sign, 1, 3 halves, 7/4, 15/8, 31/16. I want to know if that particular sequence converges. So we've got, so far a sequence, Sn looks like 1 3/2, 7/4, 15/8, 31/16, and so on. By looking at those, I can't really tell. I need some sort of formula for the nth terms. So instead of looking at those as numbers, I'm going to see if I can find some sort of formula. These numbers are really close to 2, aren't they? So let's see how close to 2 they are. Right? This 31/16, 32/16 would be 2. So this is equal to 2 minus 1/16. The 15/8, that's almost 16/8. So that's going to be 2 minus 1/8. 7/4 is almost 8/4. It's 1/4 shy of 8/4. And 3/2 will be 2 minus 1/2. So let's think of that 1 as 2 minus 1. So I think each of these terms is 2 minus whatever the current denominator is. And the denominator is a power of 2. 2 to the 0, 2 to the first, 2 squared, 2 cubed, 2 to the fourth. And say the 1, 2, 3, 4, 5, the fifth term has a 2 to the fourth in the denominator. So if you were going to predict a formula for the nth partial sum, it should be 2 minus what? 1/2 to the n minus 1. So from this pattern, you notice that the nth term should be 2 minus 1 over the power of 2, which would be 1 fewer than the term. What that is now is a general formula that describes this list of numbers. We've got a general formula for the nth term. And we know that a sequence converges if that nth term has a limit. So let's take the limit of that as n goes to infinity. And what do you get as that limit? 2. Because n goes to infinity, 2 to the infinity gets infinitely large, 1 over infinity goes to 0. So this is like 2 minus 0. So this is 2. So here's our conclusion. The sequence of partial sums converge to 2, so our infinite series converges to 2. So the series 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 adds up to exactly 2. Not to kind of 2, to exactly 2. The sequence of partial sums converge to 2. This particular series can be written in closed form with the summation notation like this. That series is the same thing as, here's our sum. Let's see, that's k is equal to, it doesn't matter what I started with. Looks like I got powers of 2 there. So if I want my first one to be a 1, then I would start my counter at 0. So that's one way of saying this list of numbers added together. We've got that converges to 2. It's not that easy to come up with this formula right here. Like that example that I had for you, 1 plus a half plus a third plus a fourth. That's kind of hard to come up with a formula for the nth partial sum. But to show you an easier example where it's kind of clear that the nth partial sum doesn't converge, let's look at the following series. Here is a divergent series. The sum from k is equal to 1 to infinity of terms that look like negative 1 to the k. If we write out a few terms, when k is 1, I have negative 1 to the 1. When k is 2, I have negative 1 squared. K is 3, I'll have negative 1 cubed, and so forth. So that's going to look like negative 1 plus 1 plus negative 1 plus positive 1 plus negative 1 plus positive 1, and so on, depending on whether my term is even or odd. And the reason that this thing diverges is my sequence of partial sums are either going to be negative 1 or 0, right? My first partial sum is just negative 1. My second partial sum is negative 1 plus 1. My third partial sum is negative 1 plus negative 1. The fourth partial sum is back to 0, right? So our sequence of partial sums does not converge. This is like similar to the sequence that I put for you on your test to explain why this doesn't converge. It bounces back and forth between negative 1 and 0. I don't get a limit, right? This diverges by oscillation. I can't get this thing to... All right, so let's do another one of these. Consider the series that looks like the sum from k is equal to 1 to infinity of 1 over k times k plus 1. I want you to see if you can construct the sequence of partial sums for this series and use that to determine whether this converges or not. I'm going to tell you this series does converge. But I do want to see if we can read this notation. Let's write out what the series is, then let's write out the sequence of partial sums. So here's what the series looks like. First, if k is 1, I have, oops, let me put my formula in here. If k is 1, I have 1 over 1 times 2. Now I'm adding to it the value of that when k is 2. So that's 1 over 2 times 3. Now k is 3, and I have 1 over 3 times 4. So it's a half plus a sixth plus 1/12 plus 1/20th plus 1/30th. Those are the terms that we're adding together. If I look at the sequence of partial sums for this, then S1 is just this first term. S2 is the sum of the first 2 terms. S3 is the sum of the first 3 terms. If I went out to here, this would be S5, the sum of the first 5 terms. Let's make that sequence and see if we can come up with a general formula for the sequence of partial sums. If we can get that sequence to have a limit, then we can say that the series converges because the partial sums converge. Okay. So S1 is just the first term. S2 is the sum of the first 2 terms. S3 is the sum of the first 3 terms. And so on, so that the nth partial sum would add up the first n of these. If I replace k with n, it would have something like that. But I don't have a formula for what that sum attains. I was able to describe how it is with a little plus, plus, dot, 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 but not a single expression to tell me what that sum looks like. If I look at the sequence of numbers that the sum actually is, my first value is a half. Then I have a half plus 1/6. So that's 3/6 plus 1/6 is 4/6 or 2/3. And that's going to be 2/3 plus 1/12. So that's 8/12 plus 1/12 is 9/12. 9/12 is 3/4. So I don't know that I can see a nice little pattern for these. Maybe the numerator looks like it's always going to be 1 less than the denominator. Or it looks like the numerator is the same as the counter on the sum, and the denominator is 1 more. Am I taking a big, bold move saying that this might look like n over n plus 1? I think I can say that. So I've got my nth term written as a formula, my nth partial sum, and I know how to take that limit. What's that limit of n over n plus 1 as n goes to infinity? Infinity over infinity, so you do L'Hopital's rule. Derivative of the top, divide by the derivative of the bottom, and you get 1. That's that ratio of the coefficients thing with the same power. We get a limit of 1. So the partial sums converge to 1. Therefore, by our theorem, so our series converges to 1. We kind of lucked up. We were able to come up with a general formula again for the nth partial sum. Questions? All right, let's go back to that second example. 1 plus a half plus a third plus a fourth plus a fifth. Why are these converging? That one sounds a lot like it. Why are those not converging? Let's look at the partial sums to that particular example. Here. So I said this was divergent. Oops, where is this thing going? There it is. There she be. I can write this like this. Right? You agree with that? Well, where the heck did it go? Come back. If k is 1, I get 1 over 1. If k is 2, I get 1 over 2, and so on. So that's how I can write it in the summation notation. And I said that this was divergent. Let's look at the partial sums and see if they give us some hint as to why this series diverges and the ones that look so much like it converged. So let's look at analyze the partial sums. S1 is just the 1. S2 is 1 plus a half. So that's 3 halves. S3 is 1 plus a half plus a third. So 3 halves plus 1/3, get a common denominator of 6. 3 halves is 9/6 plus 2/6. Is that 11/6? All right, let's look at S4. 1 plus a half plus a third plus 1/4. So these were 11/6 plus 1/4. Gosh, I can no longer do this in my head. Common denominator of 12. So it looks like I got 25 over 12. Now let's look at S5. 1 plus a half plus a third plus a fourth plus 1/5. So that's going to be 25 over 12 plus 1/5. I guess there my common denominator would be 60. So 5 times 25 is 125 over 60 plus 12 over 60. Maybe that is 137 over 60. Well, let's look at what these sums are doing. They go from 1 to 3 halves to 11/6, which is not quite 2, to something a bit more than 2. This is even bigger. This is 2-ish, but more than 2 1/12. Add one more term. Let's look at S6. So we're going to take 137 over 60 and add 1/6. So common denominator there. I get 147 over 60. So that's, what is this? This one here was 2 1/12. This is 2 17 over 60. This is 2 27 over 60. Do they look like they're settling down in any way, shape, or form? If I keep adding them, do you think we'll get a sum bigger than 3? Can we get a sum bigger than 4? It looks like if I just add more and more terms, it's going to keep growing. It's not going to stop for us. And that's what I mean by the sum continues to grow and get infinite. Right? So from this pattern, it looks like our sum is getting bigger and bigger and bigger, so that Sn, even though we don't have a formula for it, appears to be able to take on any value of any size. That's not quite a proof. This is just kind of a feeling by watching those. They're growing, but they're growing slowly, and they're never approaching a limit. I'm not able to write that as a formula. I don't see any great pattern going on here. We'll have other ways to show that this thing diverges. Okay, so partial sums diverge, which means our series grows without bound. So I want you to think of a series as kind of making a pile. Each day I throw in a different size to that pile, and that pile's growing. But if after time that pile, you can't see a change in the difference in its size, then we say that that series converged to whatever that size is. But here I'm going to keep adding things to the pile, and it keeps getting bigger and bigger and bigger and bigger. And then that series diverges. So what is your feeling about what you need as a basic premise for a series to converge? If you're continuing to throw things on the pile and you want that pile to stabilize at a certain size, don't you eventually have to be throwing essentially 0 on it? So one of the things that we absolutely have to have in order for a series to have a chance in heck of converging is that the nth term itself is real close to 0. But that's not sufficient, because in this particular example, these terms out here are getting close to 0. They're just not getting close to 0 fast enough. Doesn't that remind you of when we integrated? Sometimes we integrated 1 over x to a power, and we got a finite sum. And sometimes we integrated 1 over x to a power and got an infinite sum. That's exactly what's called the integral test. We'll have that in the next section. Okay. Let me throw another theorem on here for you. Let's let these two things denote two different series. if we know that this series is convergent, and we know that this series is convergent, then the sum, or any linear combination of those two series, is convergent. If this series and this series are convergent, then so is this series added to this one with one summation symbol. Well,
I
hi.
don't know, I'm really curious.
Mine does that too. When my phone got wet, it would just do that at random, or it would start playing music. Now I just leave off the counter. It's here. I'm just getting lazy. What that says is the sum of a convergent series with another convergent series is convergent. And I can also multiply them by whatever I want. I can make a linear combination. I can take some number times the first series plus some number times the second series and get a convergent series. And not only is that series convergent, you can add them up in this way. That's kind of a big deal for any math majors in here. You can't always distribute a sum, only for convergent series. Now suppose that the first series is convergent, but the second series is divergent. What happens then if I add them up term by term? They're going to be divergent, right? That's what your mama always told you. One bad apple spoils the whole bunch. If I start adding now terms from a divergent series to terms from a convergent series, the sum of those two series will diverge. Convergent plus divergent is divergent. Divergent plus divergent is divergent. But convergent plus convergent is convergent. Okay, so we saw that this series, what was this series? That was 1 over 2 to the k is convergent. And we saw that this series, which one was the one that we just did? How did we write that?
1 over k.
1 over k times k plus 1 is convergent. Now I can't add them together when the counters are different. So let me scale this one up. If I change that up, I pull this down. That's convergent and that's convergent. We showed that. So that means if I take this series, then that one's convergent. But we also saw that this series is divergent. So suppose I had this. Made that, then that is divergent. This series right here is an example of a particular type of series called a geometric series. And we're going to be able to tell whether a geometric series converges by looking at the size of the term that's going to infinity. So let's talk about geometric series. You have time? You guys doing okay? Here. The geometric series is a series of the form, let's see, do I want to start at 1 or at 0? Yeah, let's go to 1. Some constant times a number to the k or the k minus 1 power. So it looks something like a plus a times r plus a times r squared plus a times r cubed, and so on, where a is just a multiplier, a constant, and r is a multiplier. So the series 1 plus a half plus a fourth plus an eighth plus 1/16. The multiplier that moves us from one term to the other is the number r. What's the multiplier that moves me from 1 to a half to a fourth to an eighth to a 16th? 1/2. I get the next term by multiplying the term right before it by a half. That's a geometric series with r is equal to a half. The series 2 plus 10 plus 50 plus 250, that's about all I can do in my head, is also geometric. What am I using as my multiplier? Multiplying the previous term by 5 to get to the next term. Right? So a series that is formed by multiplying by a fixed number, r, is geometric. Here's another geometric series. 1 minus a third plus 1/9 minus 1 over 27 plus 1 over 81 minus blah, blah, blah. What is my multiplier here? With the negative 1/3. So a is the first term. This one has a is 1 and r is a half. The second one has a is 2 and r is 5. And this one has a is 1 and r is a negative 1/3. Those are going to be real easy to check to see if they converge. And I'm going to show you by doing this in general. I'm going to take this series here, and I'm going to form the sequence of partial sums, get that as a function of n, and help us decide when it converges and when it doesn't. So let's consider back to here. The nth partial sum is just the first n terms added together. So we're just going to add these up and stop at n. A plus AR plus AR squared plus AR cubed. Now I'm out here at the nth one. Now notice that whatever term number I'm on, the exponent is 1 fewer. That's what that's saying. So if k is replaced by n, my nth partial sum terminates with the term a times r to the n minus 1. Get up there. I need to try to get this as a formula, strictly as a function of n, not with a dot, dot, dot to it. If anybody needs any questions at home. You guys got any questions? Everybody almost awake back home? I don't know where to find my chat box again. So if you have questions, you have to turn on your mic and ask it. Somebody has something here. Cat's good, yay! Okay, go back down. Okay, so you can always holler at me if you have a question. Same to you out there. I know I'm putting all of you asleep too. You can holler at me. Okay, there's kind of a standard trick to generate the formula in closed form for the nth partial sum. What I'm going to do to this line here is I'm going to take that entire line and I'm going to multiply it by r. Multiply the whole line by r. So here's what it'll look like. If I multiply that by r, it looks like a times r. So I'm going to put it over here. If I multiply that by r, it'll look like a times r squared. And so it does this little shifting thing for me. So there's going to be a term here right before this one that when I multiply it by r, it's going to look like ar to the n minus 1. But when I multiply that particular term by r, I'm going to get an ar to the n. So multiplying that by r gives me a repeat of all of the terms except for this one. And it gives me an additional term back here. So I got an idea. Why don't we subtract one line from the line above it? Let's just subtract and see what's left. What's the order that I want to subtract them? Okay, so let's subtract the second line from the line above it. That minus that. That's why I lined them up. And so if I subtract, that minus that will give me 0. That minus that will give me 0. All of them will give me 0 except for the first one. It will be there. And the last one will be a minus. That particular subtraction allows me to get rid of everything except for the first term from the first line and the last term from the second line. And now I'm going to treat that as an equation and solve for Sn. So I'm going to pull out the common factor of Sn on the left. I'm also going to pull out the common factor of A on the right. And now I'm going to divide by this 1 minus r and get Sn by itself. That tells me any geometric series has as its nth term a times 1 minus r to the n over 1 minus r. That's a closed form for Sn. If this has a limit, then the sequence or then the series converges, right? Because the sequence of partial sums will converge. So in order for the sequence of partial sums to converge, we need this limit of the nth term to be finite. We need this limit to be finite. And there is only one term that depends on n. The other ones don't. There's the only term we need to worry about. So what's going to make a number r to the n have a limit? Right? One example, r was a half. One example, r was a negative 1/3. One example, r was 5. Would 1/2 to the n, 5 to the n, negative 1/3 to the n of those, which of them has a limit as n goes to infinity? Right, in our examples, we had things like our multiplier is a half, right? R is a half. R was 5. R was a negative 1/3. Do any of those, does 1/2 to the n, 5 to the n, negative 1/3 to the n, what happens to those as n goes to infinity?
The fractions go to 0.
The fractions will go to 0, but 5 to the infinity goes to infinity, right? So these will go to 0. This one goes to infinity. What if I had a 3/2 as my multiplier? Well, then I'd have a 3 to the n over a 2 to the n. Which one grows faster, 3 to the n or 2 to the n? So what happens to the limit if it's top heavy? Goes to infinity. We need some sort of fraction in here, some r, some ratio, to vanish when n gets big. So we need it to be bottom heavy. In other words, we need that ratio to be something smaller than 1. But that's smaller than 1. We need it also to be bigger than negative 1, right? So this limit is finite only when that multiplier r, whether it's a positive number or a negative number, is smaller than 1. What if it's equal to 1? What happens if I just take 1 and keep adding more and more and more? Well, I got trouble if it's 1, right? If my multiplier is 1, then I have a series like 1 plus 1 plus 1 plus 1, or 2 plus 2 plus 2 plus 2 plus 2, right? Those grow without bound. So if r is equal to 1, it doesn't have a limit. If r is bigger than 1, it doesn't have a limit. Only if r is a number between negative 1 and 1. A geometric series converges if its multiplier is a number strictly between negative 1 and 1. And I can tell you what it converges to. It converges to this. That's our Sn. These things go to 0 if r is smaller than 1. If r is smaller than 1, then this limit here that term's going to go to 0, and we just get a over 1 minus r, which is the sum of any geometric series. So now I'm going to write that right here as a theorem. Geometric series it looks like the sum from k is equal to 1 to infinity of a r to the k minus 1 converges only if the multiplier is between 1 and negative 1, and it converges to S, no longer subscript because that's the sum of the series now, A divided by 1 minus R. For the few series whose sum we can actually find. So in our original example, see if I can find that. In our original example, we have this geometric series, 1 plus a half plus a fourth plus an eighth, which is this one. Our multiplier is a half. That's smaller than 1. So the sum should be A over 1 minus R. A is the first term, so in this example, A was 1. R is a half, so A over 1 minus R is 1 over 1 minus a half. So that's 1 over a half. And by gosh, by golly, that's the 2 that we got right there. Okay? So if we can recognize something as being geometric, then we can find its sum if we decide that it converges. Come back down here a little bit. So we got to train ourselves to recognize which series are geometric. If I write it like this, it's kind of clear. Okay, so I'm going to write some series down here. You tell me why it's geometric. In other words, take it from its summation form, write out the pattern of terms, and show me that it looks like the terms are a multiple of R away from each other. If that number R is an absolute value between 1 and -1, or smaller than 1, then it converges, and then you can tell me what the sum is. So the first one, I'm going to just write it out as the formula looks. So my first one's going to look like the sum from K is equal to 1 to infinity, and I'm going to have 5 times 9/10, and up here I'm going to have a K minus 1. What I want you to do is write out, say, the first so many terms. But don't put them in simplified form. So the first term is found by replacing K with, in this case, 1. So if K is 1, I have 5 times 9/10 to the 0 power. What's 9/10 to the 0?
1.
So I just get the 5, right? If K is 2, I have 5 times 9/10. If K is 3, I have 5 times 9/10 squared. And so on. So it has the form that I described up here. Take a number, add to it that number times R. Add to it that number times R. Then that number times R. Right? So what's my multiplier here? 9/10. A is 5, R is 9/10. Since that number is smaller than 1, this converges. And it converges to A divided by 1 minus R. So I put the 5 in where the A is, and the 9/10 where the R is. So that's 5 divided by 1/10. Do you agree that that's 50? Those numbers add up to exactly 50. So that means that, right, the 5's a constant. If I pulled it out, that means that this,
I think someone said something in the chat.
okay, thanks, where did I find the chat again? Where did I find the chat?
Yeah, there it is.
Here. Thank you, Kat. I agree. You've seen geometric series when we talked about writing a decimal with the little bar over it, right? What is 0.3 with the bar on top of it mean? But what fraction is that? That's 1/3, right? That converges to 1/3. Well, let's write it as a geometric series. That's 0.3 plus 0.3 plus, what do I want to do? 0.03 plus 0.003 plus 0.0003, and so on. So it looks like to get from here to here, I have to multiply by 1/10. So this is A, and R is 1/10. 1/10 is smaller than 1, so it converges. And it converges to A over 1 minus R. A was 0.3, and R was 1/10. So it's 0.3 divided by 0.9, multiply top and bottom by 10. So that's what makes that converge to 1/3. What's 3 times 1/3? So if I multiply this by 3, 0.9 repeating is exactly 1. Not close to 1, it's exactly 1. Just like this is not close to 1/3, that's exactly 1/3. That's an example of something that's infinite, but finite. It's an infinite decimal, but a finite sum. Okay. All right, so here's another one. Let's look at it as the sum from k is equal to 1 to infinity. Let's put a 3 to the k on top and 4 to the k plus 2 on the bottom. And my claim is that that's geometric, even though it doesn't have the same pretty form like here, a times r to the k. We can rearrange it and make it look like that. What I want you to do is write out the first so many terms and see if we can determine what the multiplier is, and what the first term is, and so forth. Don't crunch your numbers, just kind of write it out. Like when k is 1, I get 3 over 4 cubed. Now it's a series, so I put a plus sign here instead of a comma. Now k is 2, so I get 3 squared over 4 to the 4th. Then 3 cubed over 4 to the 5th. 3 to the 4th over 4 to the 6th, and so on. So the a is always the first term. A is 3 over 4 cubed. What's the r? What am I doing to get from here to here, here to there, here to there? What's my r? 3/4. Multiply top by 3, multiply bottom by 4. So does this particular geometric series converge or diverge? converges because r is smaller than 1. And it converges to a over 1 minus r. So 3 over 4 cubed divided by 1 minus 3 over 4. 3 over 4 cubed divided by 1/4 is 3 over 4 cubed times 4 over 1. So it converges to 3 over 4 squared. Converges to 3 over 16. Okay, I'll give you another one, but I'm going to write it out term by term. My next example is pi halves plus pi squared over 4 plus pi cubed over 8 plus pi to the 4th over 16. That's a geometric series. What's my multiplier? The multiplier is pi over 2. The first term is pi over 2. So a is pi over 2, and my multiplier is also pi over 2. Does this series converge or does it diverge? Diverges, right? Pi is 3.14-ish, so that's bigger than 1. So this series diverges. This particular geometric series. Okay. Okay. Now, geometric series and another kind of series where you can be able to write its nth partial sum as a function of n. Those right now are the only two that we can determine if they converge, what they converge to. Some other ones we might be able to determine that they converge. But one of the things we noticed is that if anything has any chance of converging whatsoever, you need the terms that you're adding at the end to be very, very small. If the terms that you're adding at the end are pretty big, don't go to 0, then the series doesn't have a chance of converging. We're going to call that a test for divergence as opposed to a test for convergence, because all it tells us when it doesn't converge. We can have terms that go to 0 at the end, but the sum isn't finite, right? So this is going to be a big deal for us. It's going to be called a test for divergence. Whether k starts at 1 or whatever. If you take the limit as k goes to infinity of whatever the formula is for the kth term, if that limit is not 0, then the series diverges. I'm hiding this from you. If the limit is 0, then we know nothing. Maybe the series converges, maybe it diverges. But I do know if we start adding big things at the end, or non-zero things at the end, they're going to keep growing. If I throw $1 into a pile every single day, my pile is going to grow infinitely large. But if I throw $1, then a $0.50, and then a fourth of that, then a eighth of that, and so on, that'll eventually converge. Okay? All right, that's where we pick up in section 3. I still want to show you a couple more examples of finding the nth partial sum, but I'll let you maybe find it by exploring some of the examples on web work. I think I might have the web work up there for you. All right,
You
so just
don't.
let me know what you need.
You don't have a web workup. Patty? Can you hear me?
Anybody back here have any questions? Any of my? Again. Everybody at home doing okay? Good, good. I'm gonna have a web work up. I'll go work on it right now. Put a web work up as soon as I get back to my office. Thank you guys. Thanks for bearing with me while I got this thing set up. I don't know how to stop the recording. There we go. All right, I'm gonna stop the share and I'm gonna stop the recording unless you have a question. Stop the recording somehow. Video. Share. I'm at 9, yes, you should be able to finish some at 9. All right, ending it, I'm ending it. So stay warm.